What's up, math magicians? We got section 3.8 solving nonlinear systems, and welcome to the end of the chapter. Let's do a little bit of review. We're going to solve using substitution. You remember blue equation, red equation. Here we go. It looks like this. I can see x, and I think what I can do is I can get x all by itself. So I'm going to add 3y to both sides to get this new version of the blue equation. So what does x equal? X equals 3y minus 12. 3y minus 12. 3y minus 12. And that's what exactly we're going to put right here instead of x. We're going to rewrite the red equation, and instead of x, I'm going to write the blue equation, 3y minus 12. So there it is, 2 times what used to be x plus y is equal to 11. Now, when we distribute, we get something completely different, and then it's neither red nor blue, so we'll call it green. And then we distribute, combine the like terms to get 7y, add 24 to undo the subtraction, undo the multiplication, and you get y is equal to 5. Now what you can do with that y value is you can plug it back into, say, I don't know, the red equation. You could have used the blue equation if you want, but I used the red. And there it is. Or you could even use this version right here. Put the y into this. I'm going to just use the red. 2x plus 5 is equal to 11. And using that, you can figure out that x is equal to 3. And this is how you present your one solution. This is the one place where the two lines intersect at 3, 5. There's the two values that will work in both of these equations at the same time. Now let's just remember what elimination looks like. Elimination, let's do the same exact problem except using a different technique. Elimination, let's see, I'm going to multiply. I noticed that this y value, if I multiplied this bottom equation by 3 and added it to this equation, the y's would eliminate. So this red equation times 3 is this equation, 6x plus 3y equals 33. And so then when we take this and add it to red plus blue, it's going to give us 7x. The y's drop out, and negative 12 plus 33 is 21. Undoing the multiplication, we get x is equal to 3. Just like we did before, x is equal to 3. So, and then you can use all your Algebra 1 stuff to get the y value of 5. And there it is. Now if you wanted to graph, that'd be fine too. You could, this is what it looks like on Desmos. The two lines intersect and add 3, 5. There it is. Those are the three. That's your solving linear systems review. We're going to solve nonlinear systems, meaning we've got x squared now. That's really okay. It's not a whole lot new. We're going to apply the work we had with quadratics with what's going on here. Y is equal to x squared minus 5. X minus y is equal to 3. Let's use substitution. Excuse me. So we've got y is equal to x squared minus 5, and that's what we're going to put here instead of y. So x minus x squared minus 5 is equal to 3. Distribute the subtraction, we get that, and then rewriting it so that it's all equal to 0 in descending order, we get this. Now I think what I'm going to do is multiply all the terms on both sides by negative 1 so that I can get x squared minus x minus 2 is equal to 0. And now I can split the middle. You might ask yourself, what two numbers multiply up to negative 2 and also add up to negative 1? Oh, I know. Negative 2 and positive 1. So there it is. Finding the greatest common factor of x squared minus 2x, that's x. And then you're left with x minus 2. Greatest common factor, it's only just 1. So you can write a 1 right here if you really like to make it fit the pattern. And then you have x minus 2. So what are you left with when you factor out x minus 2? You're left with x plus 1. And there it is, x plus 1, x minus 2. Now, there are two x values. That means x could equal negative 1 or x could equal positive 2. And so therefore, you have to take each one of those solutions and plug them back and find their corresponding y values. So if x is negative 1, that means here that y is equal to negative 4. And if you had x equals 2, that means that y would equal to negative 1. So you can see there's a solution set here. There are two different locations on the graph. There are two different ordered pairs that satisfy both this system. The first one has the x value of negative 1 and y value of negative 4. The second one has an x value of 2 and a y value of negative 1, as we calculated here. Let's solve using elimination. But actually, before we do that, I just wanted to drop for an audio check right now that my favorite musical is Hamilton. Anyone else seen Hamilton? Not the senior. Favorite quote from Hamilton is, would be definitely, "You have no control. Who lives, who dies, who tells your story." summarizes the whole thing right there. It's really fascinating. If you haven't seen it, go get some Hamilton. And if you have seen it, let me know. If you got a different favorite musical, let me know. Solve using elimination. Y is equal to x squared minus 5. X minus 4 equals 3. So this is the same system. We're just going to solve it with using a different technique. And in order to do that, I think what I got to do is I got to line everything up kind of on the left-hand side. So I'm going to move the x squared over. And now I can see that when I add these two equations together, the y's are actually going to cancel out. You get left with x squared plus x minus 2. And if you add 2 to both sides, you set it equal to 0, which is really good when you're trying to solve quadratics. And then kind of all the rest of the work falls out, just like it did before. You have to multiply by -1, split the middle, and all that. And you eventually arrive at the same conclusion as we did from before. But I just want to show you that's what that looks like. Solve by graphing. All right, well, if you want to graph all these, this is what the graph will look like. And you can see there are actually 2 intersections. Boom, boom. Because there are 2 solutions. And here they are. -1 comma -4 and 2 comma -1. Isn't that great? Oh, so fascinating. All right. So let's continue. Let's see. On the back side, we've got y is equal to x plus 3 and y is equal to 2x squared. I think I'm going to set them equal to each other. That's substitution. So this is what y is equal to. This is what y is equal. So they could both equal each other. Let's good habit for solving quadratic equations is setting it all equal to 0. So we got 2x squared minus x minus 3. Split that middle, because 2 times -3 is -6. And the factor pair that multiplies up to -6 and also adds up to -1 is -3 and +2. So there it is. I should have written out the factor pairs next time. All right, so we're going to factor out x is there, and then 2x minus 3 is here. Factor out a 1, that's the greatest common factor, and you have 2x minus 3 again. 2x minus 3 got repeated twice. That must mean that we're doing something right. So we get x plus 1 and 2x minus 3. And so therefore, when you solve it with the algebra, you get -1 and you get 1.5. Those are the 2 x values. So that means that there's actually going to be 2 solutions. You can plug them back into the original. I like the blue equation right there. That would, when you add 3, you get the y values. So there they are, the two different locations on the graph where they intersect and the 2 different solutions. Let's see. Let's do another one. Y is equal to 3x and x is equal to y squared. Whew. All right, well, I think we can use some... rearrange them both so that I'll set them equal to 0. And I'm going to multiply the bottom equation by 3 so that I get -3x and +3x. Then they will eliminate. When you add them together, we get y minus 3y squared, which is probably very similar to what we would get if we used substitution as well. Like, notice you could have just write y is equal to 3 times, and not x, but y squared. I think substitution would have worked just well, maybe even more simply than this. Anyway, you can factor out the y, and you have y times 1 minus 3y is equal to 0. And you get y is equal to 0, or y is equal to 1/3. And if you were to graph it, these are the locations where the two graphs would intersect. And these are also the values that make both these equations true at the same time. Let's check this one out. X squared plus y squared equals 19. I haven't taught you how to graph this one, but there it is. It's actually a giant circle. How cool is that? This is the graph of a circle. And then if you do x squared minus y is equal to 7, just type that into Desmos also, and you can see these are the 4 places where they intersect. So there's actually 4 solutions, and there they are, 4 solutions, 4 intersections. 2 model rockets are launched at the same time from different heights. The height in meters for the one rocket, t seconds, is modeled by y is equal to -4.9 t squared plus 48.8 t. The height for the other rocket is modeled by y is equal to -4.9 t squared plus 46.7 t plus 1.5. After how many seconds are the rockets the same height? Round to the nearest tenth. I just graphed it. I just typed in both of these equations into you can use your Inspire, you can use Desmos. This is where the one is going to go slightly faster than the other, and the other one is at a slightly higher initial height, like on a platform. So you can see this is where they intersect right here, about 0.714 seconds after they get launched. Then I just want to say, as a quick side note, that this is not actually how rockets work. This is pretending that rockets are they have like they're actually firing. So this equation right here is used for things that are being thrown in the air, and just like after you throw them in the air, they fly. They fly through the air without any additional forces. But actually, a rocket has a force acting on it for quite a while the rocket is actually burning fuel and propelling. That's an additional force, and it's not exactly a parabola, or not this parabola with this equation. But what we're going to do is we're going to pretend that rockets get fired initially, and they have all the velocity they're going to have at the very moment when they're fired off. So let's get back to solving these. Part B, I solved part A with a graph. From what height would the slower rocket have to be launched so that the rocket lands at the same time? So what we don't know is the h. So I'm going to say negative 4.9 t squared plus 40. This is just copied from before. And instead of 1.5 as a platform, we're going to have h here. And then we're going to have the other one where it's starting from the ground at a faster pace. So what we can do is I can actually solve this one for t here and get the two values for t. T could be 0, which is at the very start. That doesn't make any sense. Or t could be like, congratulations, where did you win the race? Where did the two of you tie? Where did you catch up when t is equal to 0? That's not exactly what we're looking for, although it is true, mathematically speaking. So we discard this solution right here. We're going to go with the other one at 9.959. That's when the whole thing is going to. That's when the height is equal to 0. So rockets landing at the same time. If you want the black rocket to land at the same time as the purple rocket, you got to figure out when the purple rocket is going to actually touch the ground. Purple rocket touches the ground at 0 and at 9.959 seconds. So what we're going to do is we're going to take that and put it into the black equation. Oh, this should be a different color. This is all. Okay, so we're going to take the purple result and we're going to put it into the black equation to figure out what h is. So if we need the black rocket to also touch the ground at the same time, or to land at the same time, then what we'll do is we'll put in that time, 9.959, into the black equation, and the only thing we don't know at that point is h. So that means if you calculate all this out, then the h is going to be 20.9 meters. The platform has to be 20.9 meters high in order for it to give it the extra head start that it would have needed in order for them to land at the same time. In the xy plane, this is from SAT Prep. In the xy plane, the graph of y is equal to 3x squared minus 14x intersects the graph of y equals x at the points 0, 0, and a, a. What is the value of a? Okay, so what we can do is we can actually set them equal to each other. This is a system. You can think of this as a system of nonlinear equations. And so if y is equal to x and y is equal to this, then we can just set the two of them equal to each other. X is equal to 3x squared minus 14x. And if you wanted to, you could solve that using x's, or you could actually solve them using a's, because we're going to put in a as one value. A is the x value and a is the y value. And we'll just solve for a and figure out what a is. So you could solve this with x's or with a's. I chose to solve it with a's. So that means, let's subtract a from both sides to set it equal to 0. We get this, and then the greatest common factor is 3a. Factor that out, you get 3a, and what's left, 3a times what gives you 3a squared? That's a. 3a times what gives you 15a? That's 5. So this becomes a minus 5. So the two solutions are a is equal to 0, or a is equal to 5. And so you can see here, even on the graph, what is the value of a? You can see it here. The 0, 0 is where there's one intersection as listed, and then it also intersects here at 5, 5. So what is the value of A? Why don't you go ahead and answer that question on Edpuzzle, and if you're not sure, we can talk about it in class, but otherwise, that's it. Thanks for watching. Thanks for all the hard work, and looking forward to starting that Chapter 3 project with you next class. Take care. Oh, we're going to work on this section first, and Alex, and then we'll do the project after the next class. Take care.